Hello, this is Dr. Viv. Let's discuss how to find the center of mass of objects that are continuous. So you can no longer use the discrete formula for the center of mass, which we had learned earlier, but now you'll have to use the continuous version. So for example, if you want to find the x center of mass, you would do the integral of x dm over the integral of dm. And similarly, y bar would be the integral of y dm over the integral of dm. Because there are going to be an infinite number of mass points, it's appropriate to integrate them. Likewise, z bar is the integral of c dm over the integral of dm. Now normally the denominator is just the total mass, which you can find by knowing formulas from your earlier classes for various things like triangles, the area of a triangle, the volume of a cone, or the area of a circle, volume of a sphere. So we should be free to use those well-known results. Or if you've forgotten, you can simply integrate and find out. So there's a lot of freedom in these methods. So let's take a simple example here. I have a semicircular sheet of metal. Such a object is called a lamina. The origin of that term is laminar or planar object. So we have a mass element. Now, strictly speaking, these are two-dimensional integrals, so you can take the mass element to be a small square, but it's easier to take the mass element to be a strip or a disk if it's three-dimensional. So this is a 2D object. So we'll do one 2D example and one 3D example. In a subsequent video, I have next week, I'll have one-dimensional example where the mass changes with length. So those are called as variable mass densities. Here we're going to look at uniform mass density. If it's a 2D object, the appropriate mass density to use is known as sigma. Sigma has got units of kilograms per square meter. This is sometimes called the area mass density or areal mass density. Its purpose in life is to convert area into mass. As an example, let's figure out what the mass of the strip is. The strip has got thickness dy, and it's located at a location y, and the length of the strip, it's going to be x on this side and x on that side, so it's going to be 2x. By the way, the equation of the circle involves the radius of the circle, so let's write down the equation of the circle here for future reference. X squared plus y squared equals r squared is the equation of the circle. Having drawn the strip, let's find its mass. The strip mass dm, so this is dm in that formula, that's what dm is equal to sigma times some sort of area. The area of the strip is just 2 times x times dy. So there we go. We have our dm. But now by symmetry, the x center of mass is going to be 0. So you don't have to actually evaluate an integral to find that out. It's obvious that the center of mass is going to lie on somewhere on the y-axis by this choice of axes. So let's find out what y bar is. Y bar is the integral of from 0 to r of y dm. I'm applying that definition there, divided by the total mass. So I'm calling the total mass the integral of dm, the total mass, m. This is going to be using the definition of sigma right above, y times 2 sigma x dy. So I can take out 2 sigma and m and then I'm just left with 0 to r. I don't want x. The integral is with respect to dy, so I want only y. I can eliminate x by using the equation of a circle. That equation tells me that x is equal to the square root of r squared minus y squared. So I'm going to get, and then this y is still there, y dy. That integral needs to be performed. Now if you're lazy, you can go and look it up online using various integral calculators, but this is such a simple integral that we should do it by the method known as U substitution. Actually, U substitution is what your calculus teacher would have taught you. I'll teach you a superior substitution called the U square substitution. If you have a U substitution, if you set r squared minus y squared equals u, you're still going to be left with the square root. I don't like that square root, so I'm going to use the U squared substitution. That goes like this. You're going to set whatever is under the square root to be u squared. This time when you take the square root, you're going to end up with u. When I differentiate both sides, I'm going to get negative 2y dy is equal to 2u du. Then I'm interested in y dy because that's what I want to replace. So y dy is going to be negative u du. Now what about the limits? When y equals 0, u squared is going to be r squared, or therefore u is going to be r. When y equals r, then I'm going to get r squared minus r squared, which is 0. So u will be 0. Let's go back now and work out our answer. Now meanwhile, separately, the mass of the object, well, you all know the formula for a semicircle. It's just 1/2 pi r squared. So that's just 1/2 pi r squared times the mass density sigma. All right, now for the home run. Y bar is 2 sigma over m. I will hold off on substituting for m. I'll put that at the end, okay? So I get 2 sigma over m. The integral, the lower limit is going to be, when y equal to 0, u is r to 0. R squared minus y squared is just u, because under the square root, it's just u. And y dy is minus u du. Now observe that there's a minus sign here. I can use that to switch the order of my limits. So I'm going to get 2 sigma over m integral 0 to r u squared du. Well, that's very easy to do. It's just 2 sigma over m u cubed divided by 3, and when I evaluate u cubed divided by 3 between 0 and capital R, I'm going to get 2 sigma over m r cubed over 3. The lower limit doesn't contribute. And now I'll substitute for capital M. So I'm going to get 2 sigma r cubed over 1/2 pi r squared sigma. Observe the sigma cancels out, and 2 and the half in the denominator goes upstairs and becomes 4. So I get 4 over pi. Sorry, there's a 3. 4 over 3 pi r, because you have an r cubed there and an r squared, so I ended up with an r. So that's our y coordinate of the center of mass, and the x coordinate is 0. Pretty nice. You would notice that this approximately looks something like 2/3, because that pi is approximately 3, so this is going to be something like 2/3 r. Wait a sec. If pi is approximately 3, that's going to be 4/9. So it's going to be 4/9 r. So it's a little below half. Okay. 4/8 would have been half. So you can make it makes sense. It's going to be a little bit over here because it's weighted more towards the bottom. The other example I have is a 3-dimensional version of a semicircle, which is a hemisphere. So let's take the trouble of drawing that. Because it's 3D, we have to draw three-dimensional diagram. Apologize for the rough drawing, but this is going to be your x hat direction, that's going to be your y hat direction, and that is z hat. This time the volume element, you have a volume element, not an area element anymore. Now again, if you were a die-hard multivariable person, you'll probably use three-dimensional integration, but we're not that crazy. So what we'll do is we'll choose, if you choose an element that's complicated, then your integration will be simpler. And so this element is the disk of width dz, and let's call the the radius of the disk to be little r. So if I draw another line there, that's going to be capital R, the radius of the hemisphere itself, and this distance here is z. So we have another equation using the Pythagorean theorem, because that's 90 degrees, and that is r squared plus z squared equals capital R squared. That can immediately be solved for little r squared. Little r squared is capital R squared minus z squared. And so we can express everything in terms of that. Now, just as we had in the previous problem a mass density sigma, now we're going to have the mass density rho. This is what you know to be standard mass density. Its units are kilograms per meter cubed, and that's called the volume mass density. Now I'll put the volume in parentheses because it's the usual meaning of density. The dm would be the mass of this disk element, so let's write that down. Dm is going to be rho times the volume. The volume is the area of the disk, which is pi little r squared, times the thickness, dz. Now, as a little aside, let's just check if this is correct. What I can do is I can find the mass of the object. Now this sometimes I like to do because just to see if the integral is set up properly. So let's try to do a little sidebar calculation. So the mass, capital M, is going to be the integral of dm. Well, that's just the integral of all this stuff. So it's an integral from 0 to r of rho times pi r squared dz. Well, for r squared, I can substitute for this from here. So I'm going to get, I can take pi and rho outside because they're simply constants. 0 to capital R, r squared minus z squared, because that's what little r squared is, times dz. And that is going to be pi rho, integrate this, let's get r squared z minus z cubed over 3 between the limits 0 and r. That's going to be pi rho times r cubed minus r cubed over 3, which is 2 pi over 3 r cubed rho. So that makes sense because the mass is just equal to half the volume of a sphere, which is also called a hemisphere, times the density. Check. All right, now let's go about finding the center of mass of this object. The calculation is actually simpler than the two-dimensional case, paradoxically. So let's figure it out. Z bar is what we need. By the way, x bar and y bar are 0 by symmetry. Always symmetry should be exploited to the hilt. So that's going to be integral 0 to capital R z dm upon the total mass m. let's calculate this. The dm, I'll take out the pi and the rho again. Pi rho over m, 0 to r. I have r squared, and then I have a z. So r squared z dz. Now once again, I'm going to use little r squared equals capital R squared minus z squared. So let's just do that. R squared minus z squared times z dz. At this point, it's just a couple more lines. So let's do the math. That's r squared z. So when I integrate this, I'm going to get r squared z squared by 2. And that's z cubed. When I integrate that, I get z4 over 4. And that whole thing is from 0 to r. Now, only the upper limit contributes. I'm going to get r4 over 2 minus r4 over 4. So that's just r4 over 4. So I get pi rho over m, r4 over 4. And as the last step, substitute for capital M from here. Capital M is just given there. So let me just write all that. Pi rho r4 over 2 pi over 3 r cubed rho times 4. Notice that there's just one factor of r. The crutch of density vanishes. A pi cancels out. And so that's just 3/8 r. 3/8 is a little bit even less high than that. So it's getting weighted down even more by the bottom.